The mission of a railroad is to get passengers to their destinations as safely, comfortably, and quickly as possible. The passenger car, which had an advantage in terms of comfort, has given up its leading role to electric multiple unit, or EMUs, due to the demand of the times for greater emphasis on speed. So why do EMUs have such an advantage over other vehicles in terms of speed? Basically, the lighter the vehicle and the higher the output, the better the acceleration and the higher the maximum speed. What are the differences between electric locomotive-hauled passenger coaches and EMUs? Let's compare JNR's mainstay EF58 hauled passenger train in the mid-Showa period with the rapidly emerging Series 80 EMUs. At that time, it was common to see long 15-car electric train sets running, and the 80 series had a configuration of 6 motive cars and 9 trailer cars. The motor car output was rated at 350 kilowatts for continuous operation and 554 kilowatts for a 1-hour rating, and in actual operations, the trains ran with the 1-hour rated current. With 6 cars, the continuous rating reaches 2,100 kilowatts, and the 1-hour rating is 3,324 kilowatts. On the other hand, the EF58 locomotive has a 1-hour rating of 470 amperes at 1,900 kilowatts, and the current can be increased by the driver using the throttle control. During departure, the throttle was advanced when the motor current dropped below 500 amperes, with an average acceleration current of about 520 amperes. This meant the train was operating with a slight overcurrent, around 10% higher than the 1-hour rating of 470 amperes. In terms of output, it was approximately 2,100 kilowatts. Given the insulation materials at the time, neither the EMUs nor the locomotives were being overly stressed. However, with such a significant difference in output between the train sets, the performance gap was evident, especially in acceleration. A look at the acceleration curves makes it obvious that even with double heading, the performance still falls short. The difference in performance between electric trains and electric locomotives can generally be attributed to the difference in output. But what about the comparison between electric trains and diesel trains? In the 1950s, diesel trains were highly anticipated on non-electrified regional lines as they could run fast without producing smoke, just like electric trains. Before long, they became the star express trains of rural areas. Let's compare 12 car formations. In the 82 series, except for 4 cars with 1 engine, all other cars have 2 engines, making all of them motive cars. On the other hand, the 151 series has a 6M6T formation, with only 6 motive cars. The 82 series has a formation output of 3,600 horsepower, while the 151 series has 2,400 kilowatts, equivalent to about 3,220 horsepower. Surprisingly, the electric train is outperformed by the diesel train. Moreover, according to modern output standards, the 82 series has 210 horsepower per engine, giving it a total formation output of 4,200 horsepower. Now, let's consider the weight. The 151 series weighs approximately 476 tons when fully loaded, while the 82 series weighs around 578 tons. As expected of a DC electric train, it is significantly lighter than later AC-DC dual-mode trains, being over 20% lighter than the diesel train. However, in terms of output, the 151 series is more than 20% weaker. So, how does this affect the competition? Will it be a close match? Let's look at acceleration performance. Initially, the diesel train takes the lead thanks to the power of the torque converter, but it is quickly overtaken, and the gap widens dramatically. Except for right after starting, the electric train wins by a landslide. The acceleration curves show a significant difference. Why does such a disparity exist? In fact, the new electric trains, which were referred to as new performance trains at the time, benefited from advances in insulation materials, which improved the heat resistance of the motors and allowed them to handle high currents for short periods. The 151 series, rated at 2,400 kilowatts, was running with currents that exceeded the 1-hour rating by over 1.5 times. During test runs before the debut of the Kodama service, the setup was so severe that it even caused resistor burnout incidents. These trains displayed nearly double the acceleration performance compared to their rated operations. This characteristic of electric motors, which can temporarily push their limits even at the risk of damage, is something that engines, while somewhat capable of enduring overloads, cannot match in practical use due to the high likelihood of frequent failures. What about the output? This chart illustrates how effective output during acceleration changes with the train speed. It is clear from this that, unlike the 82 series, which only increases output as the speed rises, the electric trains deliver high output from mid-range speeds. At peak, the output exceeds 1.5 times the rated value, surpassing 4,800 horsepower for the entire formation. For a direct comparison, let's present the output per unit of weight. Even with this comparison, the 82 series cannot compete. What needs to be emphasized here is that electric trains deliver their maximum output at mid-range speeds. In contrast, diesel trains reach their maximum output only at their top speed. Electric trains can utilize their maximum output at the speeds most frequently used during acceleration. At 80 km per hour, the effective output of electric trains is actually twice that of diesel trains. On the other hand, diesel trains achieve their maximum output at top speed, which means they cannot effectively utilize engine power during the critical acceleration phase. The impact of this difference on actual operation is illustrated by this running curve. On routes with frequent acceleration and braking due to point restrictions, the difference in acceleration performance at mid-range speeds becomes quite significant. Although the difference in acceleration power has a relatively small effect on travel time, a significant difference in acceleration performance can still have an impact, even if the maximum speeds are the same. Furthermore, this difference in acceleration performance directly affects the balancing speed, which refers to the speed at which a train can maintain while climbing an incline. On mountainous routes, the difference in balancing speed has a greater impact than the difference in acceleration force. The vertical axis of the acceleration force curve uses a unit called kilogram force per ton. To give a familiar example, the acceleration force when the speedometer reading increases by 1 km per second is approximately 28 kg force per ton. This unit corresponds directly to the gradient expressed in per mil. In terms of the speedometer, a train that reaches coasting at a 28 per mil gradient will decelerate by 1 km per second. On the other hand, a train with an acceleration force of 25 kg force per ton at 90 km per hour can climb a gradient of 25 per mil at that speed. When comparing the acceleration force curves of the 151 series and the 82 series from the perspective of balancing speed, the performance difference is truly astounding. This performance gap can still be manageable at a gradient of 10 per mil, considering actual operating speeds, but becomes quite challenging at 16.7 per mil and problematic at 25 per mil, where the difference is doubled. The running curve clearly shows how even gentle gradients can cause significant difficulties for diesel trains. With such a pronounced gap, it is impossible to maintain the prestige of express trains, even during the mid-Showa era of Japan National Railways. However, this raises a question: why is it that electric locomotives don't undergo such overload operation, unlike electric trains? The reason is clear: electric locomotives are limited by adhesion constraints, making such extensive overload operations either unnecessary or simply impossible. While it is possible to push locomotives to their adhesion limits when hauling short trains, back then, it was common for passenger trains to have 12 to 15 cars. When a locomotive with around 2,000 kilowatts is hauling such a long train, the extended periods of power operation lead to temperature limitations in the traction motors. On the other hand, EMUs can take advantage of their high acceleration performance, regardless of the train formation, to shorten power application time. If the motors overheat, they can be cooled down while coasting, allowing for repeated overload operations. However, when the power application time is prolonged, even electric trains cannot handle such overloads, as seen with the 151 series struggling at Sino-Hachi, which I described in another video. Later, the motor output was increased from 100 kilowatts to 120 kilowatts, resulting in the 181 series, but as electrification expanded into more mountainous regions, the current limit was set to about 1.2 times the rated value. Consequently, the acceleration performance on flat tracks did not differ much from the 151 series during the Kodama era. This demonstrates how much high performance was demanded of the 151 series.